I of t 2 e power minus t 2 of t ampere. Okay. See, as I said earlier, this problem is based on the Parseval's theorem. But we are not going to prove the Parseval's theorem. I am going to take the frequency domain expression for calculating the energy. So whatever given here, it's current. So we know power is I square into R. Okay. So here the resistance value is 2 ohms. Okay. So first let me find out I of omega, which is 2 over 1 plus j omega. Is it right? We need, for frequency domain energy expression, we need I omega, absolute of I omega the whole square. So we can write like this: I omega multiplied by I omega conjugate. So 2 over 1 plus j omega. This is multiplied with 2 over 1 minus j omega. Okay. So numerator 2 into 2, it's 4. Denominator 1 plus omega square. This is actually absolute of I of omega the whole square. So now let us write the energy expression in the frequency domain. This is not a verification kind of problem. If you go through the problem, they are asking us to find out the energy, the total energy, okay, in the entire frequency band. That means from minus infinity to plus infinity radian per second. What is the energy? That we have to calculate first. Then they have given a specific band minus 4 to plus 4. Okay. For example, I'll just take, this is minus 4 radians and this is plus 4 radians. Say the total energy. Let me mention the total energy. W 2 ohms. Let me mention what is the energy in this particular band, that is W. So we need to find out the ratio W over W 2 ohms. Okay, this is what we are going to find out. So first let us find out the total energy. I'll write the Parseval's theorem expression. W 2 ohms. This is current equation. So the energy value, that is multiplied by current. So can somebody say the general formula? 1 over 2 pi minus infinity to plus infinity d omega into the resistance value R. In this case it is 2. If you want, you can write it in 2 steps. First you write R, then you substitute here. So you can cancel this 2. Okay. Yeah. 1 over pi integral minus infinity to plus infinity absolute of I of omega. Okay, absolute of I of omega, I think it's 4 over 1 plus omega square. So I just want to explain this 4 over 1 plus omega square. So what I did, I just wrote a simple MATLAB code. This is omega. Okay, omega. I'm not taking minus infinity to plus infinity. I'm just taking a small range, minus 10 to plus 10. Okay, the increment is 0.5. So from minus 10 to plus 10. Okay, the increment or step size is 0.5. I have written this I expression 4 in the numerator divided by 1 plus omega square. So this is a simple for loop in MATLAB. Okay, if you are opening a for loop, you have to end it. So this for loop runs up to the length of this w. Okay. So after finding out w for after finding out I for each w. Okay. It's actually not w. It's omega. I have used w. I'm just plotting this. Very simple code. You can easily understand. You can take any value. I just want to take the same negative limit and positive limit. I'm running the code. You just see this is what I'm getting. You just see this is from minus 10 to plus 10. Minus 10 to plus 10. It's at 0. So when I substitute omega equal to 0, okay, we are getting the maximum value 4. Okay. If you see around y-axis, this particular curve is, this particular graph, modulus of I of omega the whole square, that is symmetric. So instead of taking from minus 10 to plus 10, you can take 0 to 10. You can integrate the portion 0 to 10, and whatever the value you get, that you can multiply it by 2. Okay, since this is symmetric, we can use this property. Okay. So what I'm doing, I'm rewriting the same equation. 2 over pi integral 0 to infinity. Even this 4 also you can write it outside. 1 plus omega square d omega. Yes. No. See, that's what I said. Power, we are calculating energy or power. The given expression is current. So how do you relate power with current? It's I square R. If it is voltage equation, as you said, we will be dividing the voltage V square by R. This is current equation. Yes. No, you understand, I am not solving this in the time domain. You can solve it in the time domain also. You will get the same result. That is what we proved in the through the previous example. But what is the problem? You can get the overall energy from minus infinity to plus infinity. You can get this value. W 2 ohms you can get. But for a specific band from minus 4 to plus 4, obviously you have to operate in the frequency domain, not in the time domain. So that is the reason. Okay, I'm just going both the total energy as well as the specific band energy. I'm calculating in the frequency domain itself. You can verify. You can use the time domain expression and you can show that the same result you are getting. The total energy, same result you are getting. So this is 8 over pi. This expression we know, this is something like tan inverse. So this is a square, a value is 1. So 1 over 1, I am not writing all those things. I hope you know this. Tan inverse omega by 1, it's again omega. If you want, you can write 1 over 1, omega over 1. Okay, I'm just skipping the step. 8 over pi. Tan inverse infinity is pi by 2. Okay, tan inverse 0 is 0. So if you simplify this, pi gets cancelled. Okay, 4 times 2 is 8. So the total energy, okay, the total energy from minus infinity to plus infinity is 4 joules. Okay, the entire signal has 4 joules energy. Now let us go for the specific band. Let me call that particular energy in the specific band as W. So the same equation, 1 over 2 pi. Instead of integral minus infinity to plus infinity, I am going for the specific band minus 4 to plus 4. absolute of I of omega the whole square, which is 4 divided by 1 plus omega square d omega. Again, this if you notice in the MATLAB program, I have taken from minus 10 to plus 10. You can take it from minus 4 to plus 4. That's not a problem. You just see, it's very simple. So again, it's symmetric. Let me clear. See, there are the previous values are retained, so it is giving error, vector size mismatch, but I cleared the previous variables. Now you just notice it's symmetric. Okay, so what we can do, again we can reuse 1 over 2 pi 2 times integral 0 to 4. This 4 also you can take it outside. 1 over 1 plus omega square d omega. Okay, so you can cancel this 2, this 2. So you have 4 over pi. Anything we left out? Yeah, yes. Yeah. Thank you for correcting. This should be multiplied by 2. This also will be multiplied by 2. Okay. Since this is current expression, so 4 into 2, 8. Okay. Over pi. This is again tan inverse omega, but the limits are from 0 to 4. So 8 over pi into tan inverse 4. Okay, tan inverse 0 is 0. So use radiant mode. Can you find out what is tan inverse 4? 1.3258 into 8 over pi. What is the result for this? 3.376 joules. This is the energy contained in the specific band from minus 4 to plus 4 radians per second. Now, as per the question, we need to find out the fraction of energy in this specific band. So what I'm doing, I'm just finding the ratio W over W 2 ohms is 3.376 divided by 4 into 100. I'm trying to express this in terms of percentage. Any answer? So what is the inference here means almost 85% of the energy lies from minus 4 to plus 4 radians per second, and in the remaining energy, remaining band, very less amount of energy, that means 15% of the energy is available. Okay, so almost 85% of the energy is contained in the band minus 4 to plus 4 radians per second. Okay, let me write that. Approximately 85% of energy or the signal components are present in the band the frequency band. -4 to +4 radians per second. Okay. I hope you understood the problem.